In this lecture, we are going to discuss the important phenomenon which we are observing in F block elements, that is lanthanoid contraction. It's very important phenomenon and a simple phenomenon. Just we need to understand that thing. That's it. Why it is very special? We know contraction means decrease in size. If you are considering atom is this much size, if the size decreases by this, the size is smaller, then we will say the size get contracted. Contraction means decrease in size. It's very normal phenomenon only. Then why we are giving much importance for this? The reason is in periodic table S block, D block, P block, F block. In general, the general trend what we are observing in periodic table is left to right. Across the period, left to right, effective nuclear charge increases. If effective nuclear charge increases, size should decrease. That is the trend we are observing generally, size decrease. Left to right, the element which is present in the extreme left should be larger in size. In the same period, the element which is present in the extreme right should be smaller in size. That is the usual trend what we are observing in periodic table. In D block, scandium, yttrium, lanthanum, titanium, vanadium, titanium, niobium, tantalum, scandium, yttrium, lanthanum, titanium, zirconium, hafnium, vanadium, niobium, tantalum, chromium, molybdenum, tungsten. In 3D series, already we have discussed how the size varies. In general, size decreases, but there is some variation. In some cases, the size increases. In some cases, the size decreases. Already we have discussed what is the reason for that. Here, after lanthanum atomic number 57, after crossing lanthanum, we have moved to cerium 58, then lutetium up to lutetium 71, then 72. See, the difference what we are observing in yttrium to zirconium, the difference what we are obtaining or what we are observing in scandium to titanium, the same difference is we are not able to obtain when we move from lanthanum to cerium. See here, yttrium, zirconium, scandium, titanium. Scandium atomic number 21, titanium 22, yttrium atomic number plus 18, 21, 39, 40. Yes. So 21 to 22, we are observing some change. It can be, so in general, left to right size to decrease. Scandium, for example, scandium atomic radius is 10 centimeter. Titanium atomic radius is 9 centimeter. The difference is 1 centimeter. Yttrium atomic radius is 20 centimeter. Zirconium atomic radius is 19 centimeter. Because yttrium 39, zirconium 40 atomic number. If the difference between the elements in atomic number is 1, if the difference between the element in atomic number is 1, then the difference in size also should be 1, because in first case we are observing only 1 centimeter. In second case also we are observing 1 centimeter. It should decrease by 1. 57, 58. From year to year, size should decrease. So, for example, if you are considering lanthanum is 30 centimeter, what we are thinking is cerium should be 29 centimeter. But in real case, atomic size of cerium is not 29 centimeter. It's somewhat around 26 to 27. 26 to 27 centimeter. For our understanding, I am giving the example. This is not exact values. So here and all the difference is same. The difference is uniform. But here lanthanum to cerium, the difference is not same. And moreover, cerium, praseodymium, neodymium, promethium, samarium, europium. So here 58, 59, 60, Here and all, the difference is very very small. For an element, another element, another element, another element, the difference in atomic size very 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 small. If you are considering cerium is 26 centimeter, praseodymium is nearly 25.1 centimeter. Neodymium is 25.8 centimeter, 25.7 centimeter. Here 25.6 centimeter. The difference is in 0.1 centimeter. Why it is arises? Here and all, for one element to another element, we are able to observe 1 centimeter difference in size. But the same case is not observing in cerium to lutetium. The reason is, when we move from scandium to titanium, scandium atom 21, titanium atom 22, one electron we are having extra from moving from scandium to titanium. That one electron enters into 3D. On moving from scandium to titanium, one electron we are having extra. That one extra electron, that one incoming electron goes to 3D. Lanthanum, cerium. Lanthanum atomic number 57, cerium atomic number 58. On moving from lanthanum to cerium, the incoming electron enters into 4f subshell. The reason why the difference is not 1 centimeter, why the difference is very small, why it gets contracted. The reason is, here the incoming electron goes to 3D, here the incoming electron goes to 4f. Once the incoming electron goes to 4f, the screening possessed by the electron decreases. Sigma decreases. If sigma decreases, atomic size, screening decreases. Atomic size decreases. Screening possessed by the inner electrons. And shielding caused by 3D electron enters into 3D, screening caused by electrons enters into 4f. Screening caused by 3D is more. If 3D electron causes more screening means, from the nucleus to the valence electron, the size will increase, the atomic radius will increase because the screening is more. If screening is less means, nucleus can effectively attract the valence electron. If nucleus can effectively attract the valence electron, size gets contracted. So the reason why we are not able to observe the predicted change on 1 centimeter from moving to lanthanum to cerium is, here on moving from lanthanum to cerium, the incoming electron goes to f subshell. Once the electron enters into f subshell, it will cause poor shielding. If it is pure shielding, atomic size decreases. The decrease will not be gradual, it will be irregular. So in lanthanide, from left to right, it's nothing but cerium to lutetium. On moving from cerium to lutetium, effective energy charge increases. Means size to decrease, that is okay. But here the decrease is not uniform, it is irregular. The reason is the shielding is not proper. ZF increases. Incoming electron enters into 4f subshell. Shielding is not uniform. Due to the incoming electron enters into f subshell, which causes poor shielding, size decreases. The phenomenon of observing decrease in size due to the poor shielding of lanthanide once the electron enters into 4f subshell, that is known as lanthanide contraction. Shielding causes by 1 electron in 4f subshell, shielding causes by 1 electron in d subshell. You can write f subshell, d subshell. Which electron will cause more shielding, whether the electron enters into 3d or f subshell? F subshell is more free to the nucleus, more free to the space. D is more contracted to the on comparing F and D. D is very close to the nucleus. F is far away from the nucleus. So the electron enters into D subshell has more shielding effect. Shielding causes by one electron in D subshell is more. Due to poor shielding of 4f electron, size decreases. This is known as lanthanide contraction. Because of this, so many properties get changed. That is the reason why we are giving importance for lanthanide contraction. What are the impacts or what are the changes happened due to lanthanide contraction? That we are going to discuss in consequences of lanthanide contraction. To understand this, first we should have idea about first consequence, basic strength of hydroxide. What is meant by basic strength of hydroxide? First we should know, I should have idea about hydroxide. If you take MOH, it can be any metal OH. If you dissolve this in water, if it gets dissociated, it will produce M plus OH minus. How fast it releases OH minus, that is going to determine the basic strength. Basic strength of compound is nothing but how fast or how quick the compound is ready to lose OH minus or ready to produce OH minus. That is going to determine the basic strength. Now consider if MOH bond is pure ionic, then on dissolving MOH in water, it is ready to give M plus OH minus. If the bond is predominantly ionic, and partially covalent, then MOH, in that case also MOH will produce M plus OH minus. But on comparing this two, here it is ready to lose, here ready to undergo dissociation. On comparing this two, this will be slow. It will produce only small amount of OH minus, or we can say it takes a lot of time to produce OH minus. If the bond is predominantly covalent, and partially ionic, MOH on dissolving in water will produce M plus OH minus, but it will be very slow. So in this case, the MOH which is pure ionic, is more basic than MOH predominantly ionic and partially covalent, which is more basic than MOH predominantly covalent and partially ionic. Okay. How can we relate this? So here the bond between MOH is going to determine. Anyhow, in all the case OH remains same. Here M only changes. For our understanding, we can write M1, M2, M3. M1, M2, M3. M1, M2, M3. In all the case OH remains same. M1, if it is M1, it will form only ionic. If it is M2, predominantly ionic, partially covalent. If it is M3, predominantly covalent, partially ionic. How can we relate this? To understand the complete picture, we should have idea about Fajon's rule, and which is a part of your 11th standard syllabus. Now, what is our need for to understand this is covalent character. Covalent character is inversely proportional to size of element, size of cation. Covalent character is inversely proportional to size of cation. If size of cation decreases, covalency increases. If covalency of MOH, if covalency of MOH increases, base strength decreases. Because here it becomes predominantly covalent, it is less basic. Basic strength decreases. So common oxidation state of lanthanide is 3 plus. Hydroxide is OH minus. This is Ln represent all the lanthanides, cerium to lutetium. This is not La. La means only lanthanum. Ln is lanthanides. So general formula will be LnOH thrice. If you take cerium, it will be CeOH thrice, cerium hydroxide. Now cerium hydroxide, lutetium hydroxide. We know on moving from lanthanum, cerium to lutetium, size decreases. Here we have Ce3 plus, here we have Lu3 plus. Size decreases. If size decreases, covalency increases. If covalency increases, base length decreases. So covalency of LnOH is cerium hydroxide. I take samarium hydroxide. Randomly I am taking. Then last lutetium hydroxide. Cerium, samarium, lutetium. Se3 plus, Sm3 plus, Lu3 plus, lutetium hydroxide. So on comparing the size, lutetium will be smaller, samarium will be somewhat larger, cerium will be larger. On comparing these three, so here covalence will be more, samarium will have higher covalence than cerium. Basic strength. Basic strength means how fast or how fast it will produce OH minus. That is going to determine the basic strength. So here cerium hydroxide, samarium hydroxide, lutetium hydroxide. If covalence is more, base strength is less. It is not ready to lose OH minus. So basic strength decreases from cerium to lutetium. Basic strength of hydroxide decreases from cerium to lutetium. Okay. Next, due to lanthanide contraction, that element second transition stages and third transition stages, they become more similar in property because size of the element decreases. The remaining element from hafnium to cadmium, from hafnium to mercury, they behave like the second transition series. Actually, they are third transition series, but they behave like a second transition series. So similarity of second and third transition series. Due to similar chemical property, they are difficult to separate. Example is monocytes. Monocytes contains ions of similar size. It is very difficult to separate monocytes. Example monocytes. Due to lanthanide contractions, chemical property is similar, but they are different chemical property. So with having this idea, we can separate by using fractional distillation. Fractional crystallization or ion exchange method. And these are all characteristics of lanthanides. All the lanthanides are metals. They are soft, malleable, and ductile. They are good conductor of electricity. Oddness increases from cerium to lutetium. This M3 plus means Ln3 plus. Many M3 plus lanthanide ions are colored. Reason reason is due to FF transition. In D block 11, in transition series we have DD transition. Here we have FF transition. In F0 and F14 there will be no FF transition. So in that particular series there will be no color. That we have D0 and D5, D10 no, like that F0, F14. So F0, F14 complexes are colorless. F0, F14 species are colorless. Ln3 plus ions, wherever we have Ln3 plus ion, that lanthanide ion having same number of unpaired electron, have the same color. Same number of unpaired electron with same color. What is the meaning? If you take F1 means how many unpaired electron? F subshell has 7 orbital. F1 means 1 unpaired electron. What is the other configuration of F as only 1 electron? 1 unpaired electron, that is F13. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now F1, 1 unpaired electron. What is the other configuration? 1, 2, 3, 4, 5, 6, 7, 8. How many unpaired electron? 1 unpaired electron. How many electrons? First 7, then 6. So 13 electrons. F1 and F13 has only 1 unpaired electron. So lanthanides elements having same number of unpaired electron have the same color. So what is the color exhibited by F1? That same color will be exhibited by F3. So F2 and F12 will have the same color. F3, 3 unpaired electron. What is the other configuration of F as only 3 unpaired electron? What is the other configuration of F as only 3 unpaired electron? F11. Now see, praseodymium 3 plus. If you check the configuration, praseodymium 3 plus is F2 configuration. Praseodymium F2 and it is exhibiting green color. Thulium is also exhibiting green color, but praseodymium is F2. So what should be the configuration for thulium? Thulium should be F12 because in F2 means how many unpaired electron? 2 unpaired electron. In F12, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2 unpaired electrons. So in F12, 2 unpaired electrons. Now see, praseodymium 3 plus and the thulium 3 plus having same number of unpaired electron have the same color, green. Now check for europium 3 plus and the terbium 3 plus. Both are F7 configuration. Both are F7. So say 7 unpaired electron. Neodymium 3 plus, erbium 3 plus. Neodymium 3 plus is F3, erbium 3 plus is F11. Samarium 3 plus F5, dysprosium 3 plus F7. So this is the color exhibited by the configuration. pale pink is exhibited by F7, pink is exhibited by F3, yellow is exhibited by F5, F5 and F7. I mean 3 unpaired electron. Green is F block element will be green in color if it is having 2 unpaired electron. F block element will be yellow in color if it is having 5 unpaired electron. F block elements will be pink in color if it is having 3 unpaired electron. F block elements will be pale pink in color if it is having 7 unpaired electron. Again, magnetic properties. Most of the F block elements are magnet. In F0 and F14 it will be diamagnet. It will be diamagnetic. Other configurations are magnet because in all the other configurations we have unpaired electron. F1 to F13. In all the configurations we have unpaired electron, so they are paramagnetic. Now, what are the different type of compound we can form with lanthanum? Lanthanides are, with oxygen it will form Ln2O3, lanthanum oxide. With water, lanthanum hydroxide, hydrogen gas. With acid, lanthanum salt, it depends on the acid plus hydrogen gas. With halogen, it forms lanthanum halide. With carbon, lanthanum carbide, lanthanide halide, lanthanide salt, lanthanide hydroxide, lanthanide oxide. With sulfur, it forms lanthanide sulfide. With nitrogen, it forms lanthanide nitride. So, with this, we are completing the D and F block. If you have any doubt, you can ask. Happy New Year.